In this video, I will derive a simple explicit finite difference scheme for solution to the advection equation, examine the numerical properties of the scheme, and provide some interpretation of why the scheme behaves as it does as an initial step in understanding stability and accuracy of numerical schemes. Consider the advection equation dc by dt plus u dc by dx equals 0, where C is the concentration of a dissolved substance and U is the flow velocity of the fluid in which the concentration is travelling, i.e. the flow celerity. Let's assume that the celerity is constant and greater than 0. We know that in this case the characteristics are given by the equation dx by dt equals u, generating a family of straight lines in the xt plane of the form x equals ut plus a constant. Let's think a little more about what this means. First, we note that since u is greater than 0, information is travelling upstream to downstream. If we know the concentration at a certain point at time 0, we can follow the characteristic line passing through that point, and we know the concentration will remain constant along that line. So what does this mean? Suppose we have an initial concentration that's a triangular distribution like the one shown here. Then the concentration will move with the flow, i.e. the distribution will stay the same shape, but will move with speed u. The same is true of any initial distribution, provided u remains constant. So, this is the behaviour we hope to capture when we develop a numerical method to solve this equation. The interesting thing is, as we shall see, although the advection equation is relatively simple, and has this rather neat analytical solution for the constant celerity case, it's remarkably difficult to capture accurately using numerical methods. This is important since, if we do want to predict how, for example, a pollutant is transported in a flow, the celerity is usually varying, and we can't use the analytical solution. So, let's construct a numerical scheme to solve this equation approximately. Since we're stepping forward in time from an initial condition, we use a forward time difference approximation for the time derivative. Next, we note that since u is positive, the travelling wave propagates in the positive x direction, as we saw from the characteristic solution to this equation. We can think of this as information travelling from left to right, i.e. in the positive x direction. Knowing this, it makes sense to use a backward spatial difference approximation to dc by dx. We describe this as an upwind biased scheme, or simply an upwind scheme. We have to be careful about confusing terminology here. Here we have an upwind scheme utilising a backward difference approximation. If we consider a point on the x-axis and u is positive, then the left side, x is less than xi, is called the upwind or upstream side, and the right side, x greater than xi, is the downwind or downstream side. Any scheme that contains more points in the upwind side is called an upwind scheme. In the case of the backward difference approximation we've taken here, we have a single point upstream and none downstream. However, if u is negative, then the upwind side is to the right of xi, and the downwind side is to the left. In this case, we would use a forward difference approximation to the spatial derivative to form an upwind scheme. Returning to the positive celerity case, I'm going to introduce some notation before I proceed, which makes the equations easier to follow. We denote the concentration at point I delta x j delta t by Cij. Our approximations to the derivatives can then be written dc by dt equals Cij plus 1 minus Cij over delta t, and dc by dx is approximately Cij minus ci minus 1j over delta x. We substitute these approximations into the advection equation, giving us this expression here. We can now rearrange that to give us an update equation. We get Cij plus 1 equals 1 minus Cr times Cij plus Cr times Ci minus 1j, where Cr is a non-dimensional number called the Courant number, defined as U delta t over delta x. This scheme is known as the first-order explicit upwind finite difference solution to the advection equation. The order, of course, comes from the order of the approximations to the derivatives, which were ordered delta t and delta x. The scheme is described as explicit since values of c at the time step j plus 1 are calculated explicitly in terms of values known from the previous time step j. Explicit schemes are the simplest type of scheme to implement, since if we start from an initial condition, we can directly calculate all values of our dependent variable. We do, of course, still need to specify what's happening at the boundaries. Let's have a look more closely at how our numerical scheme works in our computational domain, which is an area of the xt plane bounded by the maximum value of x for which we're performing calculations, denoted here by capital X, and the time period over which we wish to solve the equation, denoted capital T. First, we discretize the domain as shown here, with spatial cell size delta x and time step delta t. Our scheme allows us to calculate concentration at each of the points where the grid lines cross. Thus, we start from our initial condition, which specifies values of c on the x-axis for time t equals 0. We then step through time using our update equation. We do, of course, need to know something about what's happening at the boundary, but I'm not going to go into that here. We will assume that we have a known boundary condition. Let's examine what's happening at a point on the grid numbered I in the x direction and j in the t dimension. The adjacent points on the grid for the same time step will be numbered I minus 1j and I plus 1j, and the corresponding points at the next time step will be I minus 1j plus 1, ij plus 1, and I plus 1j plus 1. We can see from our update equation that this scheme only uses the values of c at node I minus 1j and ij in calculating the value of c at ij plus 1. The 3 points involved in this calculation are highlighted in yellow. There is a triangle delineated by these 3 points, which illustrates the area within which information flows from one time step to the next. This is known as a domain of dependence. The value of c at ij plus 1 depends only on values between I minus 1j and ij. This is typical of explicit schemes, although the number of points on the grid at time step j will depend on the approximation to the derivative chosen, the two here coming from our backward difference approximation. For example, if our scheme used values either side of the ith node, we would have a domain of dependence like this. This is represented like this in some of the literature. Similarly, using 2 points either side of the ith node would give us a domain of dependence like this, which again can be represented like this. Okay, so we have our scheme, and we've thought a bit about how it's implemented. Now let's have a look at how it behaves when we put some numbers into it. In this first example, we have a value of the non-dimensional parameter, the Courant number, of 0.5. The graph shows both the numerical solution obtained using this scheme and the exact solution. We can see that the wave appears to be moving at the right speed, the peak of our numerical solution coincides with the peak of the exact solution. However, the distribution has a lower peak value and is spread in much the way that a diffusing concentration behaves. This is known as numerical diffusion, and it's a function of the numerical scheme and the values of the parameters we've chosen. In this next example, we have a Courant number of 1.2, and we get quite different behaviour. First, we can see on the left-hand side of the domain that we have small oscillations in our numerical solution, where we would expect a zero concentration. On the right-hand side, we can see larger oscillations appearing on the main distribution. Finally, we can also see that the peak of the numerical distribution is greater than and slightly to the left of the exact solution. This behaviour is a telltale sign that we have what we call an unstable solution. If we run the model for longer with these parameters, the solution will eventually blow up. It's important to be aware of this behaviour. It's one of the things you need to look out for when running a model. In this example, we have a slightly larger Courant number of 1.35, and we can see that the oscillations in this case are very large. Such a solution is unreliable, and we should simply discard it and ignore any results produced. They're meaningless due to the instability of the numerical solution. This last example has a Courant number of exactly 1, and the results are very interesting. We can see that in this case our numerical solution coincides perfectly with the exact solution. Now, you might think that solves the problem. We can simply choose a Courant number of 1 and we will have a perfect solution. That's true if the problem we want to solve is constrained, like this one, where we have a constant celerity and no other behaviours that we're trying to model. However, usually if we're modelling advection, it's coupled with other behaviours such as diffusion, and the celerity isn't constant in general. The sensitivity of the solution to the Courant number is an important subject which will be explored in more depth elsewhere. But before I conclude, I'll discuss briefly the relationship between the domain of dependence of the scheme and the characteristics. Here we see again the points on the grid involved in calculating C at node I and time step j plus 1. As we discussed before, we have a triangular domain of dependence, which is the darker shade in the diagram. We also know that the characteristics are given by the equation u equals dx by dt, which for constant u generates straight lines with gradient 1 over u in the xt plane. Now, I'm interested in the gradient of the hypotenuse of this triangle, so for convenience, let's label the point I minus 1j as A and the point ij plus 1 as B. The gradient of AB is delta t over delta x. Consider the case where the Courant number is greater than 1. In this case, delta t over delta x is greater than 1 over u. This means that the gradient of the characteristic is shallower than the gradient of AB, and thus the characteristic doesn't pass through the domain of dependence. This case corresponds to the examples in which we saw instability in the model runs. Now let's consider the case in which the Courant number is less than 1. Here, delta t over delta x is less than 1 over u, and the characteristic does pass through the domain of dependence. This corresponds to the stable case in which we saw some numerical diffusion in the model runs. Finally, for the case where the Courant number equals 1, we saw that the exact solution was reproduced. In this case, delta t over delta x equals 1 over u, and the characteristic coincides with the line AB. Thus, it's clear why this case reproduces the exact solution is because information is propagated along the characteristic. To summarise, we derived a first-order explicit finite difference scheme for the advection equation by approximating the derivatives using a forward time difference and a backward spatial difference approximation. We saw that the solution is sensitive to the value of the Courant number, a non-dimensional parameter defined as u delta t over delta x. When the Courant number is less than 1, we have a stable solution that exhibits numerical diffusion. When it's greater than 1, the solution is unstable. And when it's equal to 1, the numerical method reproduces the exact solution because the update equation lies on the characteristic line.